television. So let me give you some introduction. Well, first of all, this is the program. We have 4 sessions with 3 breaks, 2 for coffee and the HiPEAC lunch. So this is the introductory session. We are going to have our keynote, Mutlu from Zurich. Then we have 2 invited speakers. In the second session, we have the first one, Enrique Quintana from UPV, Malaysia, Spain, and 2 paper talks. After that, we will have a lunch. And we will have a second invited speaker. So Kilian Premier is from Samsung AI in the UK, and 2 more paper talks. And the final session, we will have 3 more paper talks and a short invited speaker. So I want to thank the other organizers of the workshop for the hard work on the last few months. So Valentin, that is here, José Luis, couldn't go, but I thank him again. Also, Marco Cornero, that is here, Dominique, also Elise is there. Thank you, guys. And we also want to thank the program committee that, in addition to ourselves, Manuela García from Murcia, Sam Edward from University of Edinburgh, Juliana Franco from DeMine, David Gregg from Trinity College, Dublin, Susan Toguli from Meta, Paolo Meloni from University of Calgary, Ivan Sun from William & Mary in the US, Sewan from the University of Leeds, and finally Alexander Sinenko from Google. So to start with, we have our keynote on Mutlu. So on Mutlu is a professor of computer science at Zurich. So he's also a faculty member at University, where he briefly held the record early career position. His current research interests are, you may know, in computer architecture, systems, algorithm theory, and also bioinformatics. And a variety of techniques along this group to collaborate with us invented over the years, influenced the industry and have been employed in commercial microprocessor and memory storage system. He obtained PhD and master in electrical and computer engineering from the University of Texas at Austin, and the bachelor's degree in computer engineering and psychology from the University of Michigan. So he has received many awards, just to name 2 or 3. He received the Google Security and Privacy Research Award, the Intel Outstanding Research Award, the Ethically High Performance Computer Architecture Test of Time Award, and also a healthy number of papers in top peak venues, right? In various computer systems, architecture, and activity. So his computer architecture and digital logic design courses, lecture and articles are really available in our website for the community. And his research group makes a wide variety of open hardware paths really available online. So thank you very much for coming for yours.
Thank you, Jose. My introduction. Oh, it worked off the bat. That usually doesn't happen. Okay, thanks for the introduction, Jose. Thanks for coming. I know there might be some disruption in flights, so it's good to have almost full room over here. So I'm going to talk about memory-centric computing, which I believe has a very important role in accelerating machine learning. But I'm going to take a more general approach to it in terms of why we need to move to memory-centric computing and what kind of applications it can help. And also specifically how it can help machine learning. So if you have questions, let me know. I also see familiar faces. I gave this particular tutorial at PACT a few months ago, and it took about 3 hours or so. Actually, I gave another version of this using very similar slides at Samos, if you were there in July, and it took about 5 hours or so. I don't expect this to take that long. So I'm going to skip some slides and also maybe ask you questions in terms of what you would like to really cover. So it's a reconfigurable set of slides. Okay, so I think no one argues that this statement is incorrect. Today, computing is bottlenecked by data. All important workloads are data intensive, and we're going to generate a lot more data. And we want to rapidly and efficiently process even more amounts of data. And we want to do more sophisticated things on the data going forward. You can pick your favorite application, and it's going to, I think, obey these. And this is one of the favorite applications that's the subject of this workshop. Well, a subclass of the applications that is covered by this workshop, neural networks in particular. This is a talk that was delivered by Cerebus's chief architect, Sean Lee. If you haven't watched this talk, I would recommend it. Here, basically, he talks about essentially exponential growth of neural networks in terms of compute requirements as well as memory requirements. And their solution as a startup, as the Cerebras company, is to put a lot of compute and memory together by building wafer scale chips that are this big, basically. So this is an example where compute and memory are getting closer so that you can actually do big things with machine learning type of applications. That's not exactly what I'm going to talk about, but this is an example of near memory computation, in my opinion. Limited example. Okay, but I think it's good that people are looking into things like this. And I think the second point in this slide is clearly the memory requirements of neural networks is growing significantly exponentially. But that's not, I think, just true of neural networks. There are many applications that are suffering from the same problem, if you will. We want a lot of compute and a lot of memory at the same time. And these applications are mainly bottlenecked by data. I'll give you some results later on. On the mobile end, we actually are experiencing a similar thing. A lot of applications are bottlenecked by data. I'm going to talk very briefly on genomics because I think this is actually a very interesting area in terms of how future living it is, and in terms of the components that are involved in it, including machine learning in it. I won't spend a lot of time, but basically in genomics, we have technologies today that can generate lots of data. This is an example. You can see that the high-throughput sequencing technologies have reduced the cost of sequencing the genome significantly. And more recently, nanopore sequencing technologies have reduced the cost of sequencing the genome much more significantly as well. And the cost of a genome, sequencing a genome is reducing much faster than the cost of a transistor manufacturing is reducing. That's a famous graph, and it ends at 2015, but it's continuing basically today. So basically, we have technologies that can generate a lot of data in genomics. The problem is we're really limited by our ability to accelerate the analysis, which leads to scientific discovery and medical advancements. I don't have time to, unfortunately, go over a lot of these. I'll refer you to some papers, but clearly this has many applications. We've seen it with COVID-19. Actually, the machines that I'm going to show you, this one, that were shipped to China initially at the beginning of the COVID-19 crisis, and they've enabled a very good understanding of the COVID-19 RNA, and they're still enabling a lot of good understanding. But that's just, clearly we're not just limited by limited to disease outbreaks. There are many, many things we can enable by faster and more efficient analysis of genomes. Okay, so another point I want to make over here is this is a data generator, and we have very good data generators. This is an example from the domain of genomics, and they actually are great at generating data, but they're terrible at analyzing data. They cannot process data at all, so you have to move the data generated by these machines, at least to your laptop. That's usually not enough. You have to move it to a data center that's far away. So you may be using these in Africa to understand some genomes, but you really create a huge amount of data moved all over the world to actually process these genomes. So I think this is a general trend that we have today in systems. We have very special purpose machines for data generation, and we move the data that's generated by them far away to general purpose machines that are basically suffering because they're not specialized to process the data that's generated by these specialized machines. In genome analysis, another example machine, this is from Illumina. But basically, you can replace it in some other domain. For example, in video, you have cameras, right? Cameras are also very specialized data generators, and we move that data all over the place to get to some general purpose machines for data processing. We don't have processing capability integrated into the machine or close to the machine. And I think in-memory computation in general is about getting processing capability as close as possible to where the data resides and is generated. So that's going to be the subject of this talk. And again, you can replace this with videos, you can replace it with clicks on the web. They're very specialized machines that are generating data, or your favorite example from your favorite domain. So my favorite domain is genome analysis. I like machine learning also, but genome analysis is actually a broader topic that covers a lot of machine learning as well. If you're interested in this, we have some beginner readings. I'll give you some examples of what you can do today. So we've been working with FPGAs that are tightly integrated with high bandwidth memory. This is a work that we did together with IBM. And we basically offloaded some genome analysis and weather modeling applications, some specific kernels over there to an FPGA that has high bandwidth memory, that has high bandwidth, low latency access to fast memory, let's say. And we basically see significant performance improvements. I'm not going to bore you with the details, but you can see that you can improve both performance and energy at the same time if you offload specific parts of the computation in these workloads. And again, I think other people have been seeing this. It's nothing new. This is what you can do today by offloading to near memory and also specializing the logic to the application. And I think going forward, we need to do more of these more aggressively, I would say. because this is doable today. And I will also mention that we would like to improve both performance and energy at the same time going into the future. We don't want to trade off between them. We don't want to improve performance at the expense of energy, because that's going to be a lot more important in the future. Okay, I can bore you a lot more or give you a lot more interesting things in genome analysis, but I don't have time. Maybe I'll get back to this in-storage genome filtering if you have time later on. Okay, I will mention that there's a lot of interesting things in genome analysis. One is base calling. And base calling, this is a paper that we recently released and recently presented at the Pacific Symposium on Biocomputing also. We've been looking at, there are a lot of components on genome analysis where you need to do machine learning. And one example is where you actually generate electrical signals in a nanopore sequencing device. So essentially what you get is electrical signals, and you want to convert those electrical signals to bases like A, C, T, G in your genome. And this turns out to be not an easy problem. And people use machine learning-based classifiers, especially deep learning-based classifiers, and accelerating those are really important actually in today's systems, especially if you want to get the processing very quickly. And this is an example where we worked with AMD to look at, I should say Xilinx perhaps, using Xilinx Versal machines. And if you're interested, you can find online. So I think future is a lot more specialized in genome sequencing and many other domains. Okay, so this was an example. I think there are many, many examples, but in the end, we're designing workloads that work on a lot of data. And this data is overwhelming our machines. It's overwhelming our storage and memory capability, communication capability, and the computation capability. And data is also greatly impacting robustness, energy, performance, and cost. And if you look at the fundamentals of computing, we need to have three fundamental components: computation, communication, storage, and memory. Today, they're very decoupled from each other. And not only that they're decoupled, but over the course of 80 years or so, we focused a lot on the computing units and not so much on the communication and memory units. So this talk is about rethinking how we design the computing system such that you integrate as much as possible these things, and also ensure that memory is given the proper, let's say, attention so that you can actually improve overall system performance and efficiency at the same time. So this is a picture that I drew in 2008 when I wrote my first NSF proposal at CMU. This picture looks still the same, I believe. It's essentially a multi-core system. And if you look at the system, computation is done only in the cores, which is a small component of the system. Everything else is there to store and move data. Caches, interconnects, other caches, other interconnects, memory controller, other interconnects, memory, other interconnects, storage, and other interconnects. Basically, if you do the calculation, more than 95% of the real estate of a single node today is dedicated to storing and moving data, even though we call it a computing system. So the computing chip is even not doing computing most of the time. Well, most of the resources in this picture, but I'll show you most of the time and most of the energy later on also. But yet, even though we're designing systems like this, the system is still bottlenecked by memory. I think this picture should alert us to think that maybe we're doing something wrong fundamentally in the beginning of the design of our systems. And if you don't believe my picture, this is a picture from AMD. You can see that the green box over here is L2 and L3 caches. And if you want to look at the global memory interconnect, it's over here. So basically, if you carve out everything that does storage and interconnects, cores are a very small fraction of this chip. And we keep adding more and more memory. This is the 3D stack cache that AMD is at. This beautiful technology, it's great that we're working on it, but are we doing the right thing at the system level? And not to pick on AMD, this is IBM. You can see a very similar picture, and this Apple. You can see that the chip over here that they've designed is a lot of SRAM, and then there's a lot of DRAM, and then there's a darkness we don't normally think about, which is storage. But maybe we should be thinking about it a lot more. Okay, so that was the resource example. But if you look at performance, if you look at these workloads, we examined these workloads together with Google a few years ago, and we found out that more than 60% of the total system energy is spent on data. And these are general purpose workloads. The 60% number is, I believe, an underestimate. There are actually a lot of other cases. I will talk about a work that we did with Google more recently on a neural network, their edge neural networks. And we see in some of those cases in LSTMs, for example, 90% of the system energy spent on data moments between an accelerator and main memory. But if you're interested, there's a lot more analysis in this paper that I'm not going to talk about. So my axiom going forward in this talk will be that we would like to handle data well in our architectures, because we would like to design intelligent architectures. I think people have been talking about intelligent architectures. These intelligent architectures are going to be making decisions for us going into the future. And if they're not handling data well, maybe they will not be making very good decisions. So the question, of course, becomes how do you handle data well? I think there are three major directions over here. I'm going to especially focus on this first one, on memory-centric computing, but these are also extremely important. And I believe both of them have relations to this workshop. First of all, I think we'd like to ensure that data doesn't overwhelm the components that we design. This requires across-the-stack thinking, a design of intelligent algorithms, architectures, and whole system designs. The second direction over here is more machine learning driven decision making in our hardware components. So today, our hardware components, as well as software components, are mostly designed by humans. And humans design policies or algorithms that are usually heuristic based. These techniques don't improve their decisions over time. For example, I have a memory controller in this laptop. It's doing exactly the same thing. It's making exactly the same decision all the time. It's not really changing its decisions based on experiences. So it's not learning. So it's not using machine learning as decision making. So I think we need to change that design paradigm into the future. And I think that requires a lot of acceleration of machine learning components inside each of our controllers. I don't have time to give you examples, but we've seen a lot of good examples of this in prefetcher design. Clearly, the branch predictor designs have been using perceptrons, right? That's a very simple example that has actually gone into products. But I think we need to do more. From the memory controllers, caches, memory hierarchy, storage. There's a lot to do over there. And the third one is, I think we need to express more from the higher levels of the system stack so that we can exploit different properties of data. Because data is really, there are a lot of properties of data that we have and that are not just expressed or used in the hardware today. For example, we have privacy properties, security properties, proximability properties, compatibility properties, error tolerance properties, performance properties. Almost none of that is expressed at the high level and communicated to the low level. Again, I'll pick on the example of memory controller because I love memory controllers. The memory controller, when it's trying to make a decision between scheduling request A and request B, it basically picks request A over request B based on some resource available. Row buffer is open, so I'm going to pick request A over request B. It doesn't think, is request A more privacy critical? For example, if I actually somehow isolate request A, I'll get much better security properties because it doesn't even know that information. It doesn't know which request is more security critical. So I think this is going to be a lot more important. And later today, Ataberk over there is going to give a talk on a system that we have designed that expresses these properties and an FPGA-based prototype of that system called Metasys to the lower levels. I believe these are actually interrelated, and we need to do more on this interrelation of these, but let's see going forward. So as I said, I'm going to focus on this first part. How to make systems more data-centric today as opposed to process-centric. But the other parts are how to make systems more data-driven as opposed to designer-educated decision makers. And the last part is how to make systems much more data-characteristic-aware decision makers as opposed to component-based decision makers. And if you're interested, I'm happy to talk about it, but this is a vision for the future. But if you look at this vision, I think it requires rethinking across the entire stack. All of these really cut across the hierarchy. Maybe the machine learning based controller design, you can actually do some things at the component levels, but I think in the end, you need to express things across the hierarchy. Of course, this is not going to happen overnight. I think you need to really do the research to get there step by step too. Okay, we've written papers about it too, but you can take a look at it. So let me jump into data-centric or memory-centric architectures. Even if you look at the first part, it opens up a whole new world, in my opinion. What is the data-centric architecture? Basically, you need to respect data, meaning that I think you need to move data as little as possible so that you can get good performance and efficiency. That's the first part over here. I'm going to talk about that. What I'm not going to talk about is we should really be looking into more low latency and low energy data access. I think we kind of omitted that because we focused so much on the processor. We have not focused as much on the memory today. I think this is going to be more important in the future. Low-cost data storage and processing. I will mention intelligent data management because that I think affects the first one over here. If you want to intelligently manage data, you need to process data where it resides as well. I'm going through some of these relatively quickly because we don't have a lot of time, but I'm happy to talk about this in detail. Okay, so let's jump into data-centric computing. I also call this processing data where it makes sense. Basically, you don't have to process data only in the processor. Today, you have no option. You have to move the data to the processor, accelerator, FPGA, whatever that is that's compute-centric today. You would like to be able to have the option to process the data in the interconnect, in the storage system, in the sensor, in the memory. And there are many places, as you can see, even in a simple system like this. But this is not a new idea. It's an old idea. These are some of the earliest papers that I could find. If you find new papers, let me know. From 1960s, these folks were forward-looking and they thought, oh, we should really be doing processing next to the memory. and this idea has been looked into over time. Now you can say, why is it interesting today, right? It's clearly it has been around, and it has not been successful, at least commercially. Why is it interesting? I think today we have nowhere else to escape. I would probably say this, unless we come up with a magic new technology. And usually the technologies that are interesting are 3D stacking. They put compute and memory together, which was discussed in the keynote lecture in the first day by Subhash. But basically, we're having huge problems with memory technology today, which was not present over the course of 60 years. And we're having huge problems with applications and systems. So I will mention this first one. I'll go into a little bit more detail over there. But basically, memory technology scaling is not going well. And we're having a lot of robustness issues, security issues, etc. And many scaling issues demand intelligence in memory. You need to do more computation and intelligence in memory so that you can fix these issues. I'm going to mention this. But most of the talk, I'm going to focus on the second part. We have a huge demand from applications and systems. Data access is a huge bottleneck. Energy and power are key bottlenecks today. And data movement energy dominates computation. And if you look at the history of computing over the last 80 years, we've never been at a place where these are more exacerbated. And they're going to get worse. They're not going to get better. And at the same time, we need both performance, energy, and sustainability all at the same time. You want to improve all metrics. The question is, how do we do that? So basically, we're squeezed by technology at the bottom and also application and systems at the top. And they're pushing us more to do something else with our systems than what we have been doing so far. Now, let me give you the hope, let's say. So today, actually, people are, because of these, in my opinion, people are examining new technologies. This is hybrid memory cube. It's essentially 3D stacked memory plus logic technologies. You can see that there's a logic layer underneath and there are memory layers, and they're connected to each other with high bandwidth, low latency, reasonably low energy connections. And as a result, you can put computation underneath memory. So that's an enabling technology potentially. And people have been experimenting with automata processing. But more recently, this is the AccML company who are based in Grenoble. And these folks actually put computation inside the DRAM chips. Hopefully, I'm going to talk about that. If you miss what I talk about, Juan is going to give a talk in this workshop in the first, I think, second session, one of those sessions. So talking about accelerating machine learning using these chips, real chips. And also major manufacturers like Samsung, Hynix, they've been actually developing DRAM chips that can do processing inside the DRAM chips or inside the modules, as you can see over here. I'm going to talk about that, hopefully. So basically, this is already happening, in my opinion. The question is, will it be sustainable? And will it actually become general purpose like how GPUs have become general purpose in the last 25, 30 years, if you will. In my opinion, memory-centric computing the development of that is becoming relatively similar to GPUs. And we need to have ways of taking advantage of these hardware that is coming up. That was like GPU-like hardware like 25, 30 years ago, if you will. There's some differences, of course, but give or take, that analogy holds. Okay, so I'm going to talk about these. But basically, people are building real chips that can do computation. And Alibaba is an example of a real systems company that has done that for recommendation inference. Okay, and there are many other experimental chips and startups that I'm not putting over here. Okay, so let me, any questions so far? If you want to stop me, feel free to ask questions. Okay, so let me cover push from technology relatively quickly. So we're having a lot of problems with technology, and we've been writing a lot of papers that are interesting, actually. Other people have been writing a lot of papers. So what is the problem? Basically, as we scale the technology to smaller nodes, memory is becoming much less reliable. This is an example correlation experiment that we did with Facebook. Basically, we analyzed all the memory areas that they have in all of their systems. There's a lot of memory, a lot of systems all over the world. And this is a graph that we put in our paper that shows that the chip density that is employed in the server highly correlates with the failure rate of the server. Don't worry about these exact numbers. You have to read the paper to figure out what those are. But in the end, if you have a chip that's denser, a DRAM chip that's denser, you get more errors. Why? The cells are smaller and the cells are closer to each other. And this is present in real data, as you can see over here. And we're not the only ones showing this. There are papers from AMD and other companies, and also supercomputers that are showing similar things. So basically, memory is becoming less reliable. And we've also been doing a lot of experiments using FPGA-based infrastructures like this to understand these memory errors. If you're interested, you can take a look at them. And we have refined these infrastructures. And we've looked at a lot of errors. One example error is RowHammer, which you may have heard of, which is the fact that you can predictably induce errors in most DRAM memory chips. Now, this is something that clearly should not happen, right? You should not be able to induce errors in any chip, let alone DRAM chips, and let alone doing it predictably. So this is an example of a technology scaling issue that was not present before. This appeared in 2012 or so, and we're still struggling with solving it. So just to give you an idea of what this is, essentially memory consists of rows. And if you access one row repeatedly, you activate that row, you apply high voltage to that row. And then if you close it, you apply low voltage. And if you keep doing this repeatedly, high voltage, low voltage, high voltage, low voltage, which is a valid read sequence in DRAM or any memory, you get some adjacent cells corrupt. So basically the data that you stored in adjacent rows gets corrupt. Clearly this should not be happening. And again, this is an example of a memory technology scaling issue. Okay, and all chips are vulnerable today, actually. This is data from 2012, but today, if you test all chips, based on what we know today, you can see that you get these errors in all chips if you bypass the mechanisms that are put to overcome this. And this is actually a reliability problem, but it's also a system security vulnerability because folks have figured out how to use those bit flips to actually take over the system, either to become root, for example, or to leak confidential data that they're not supposed to leak. So they're very, very interesting things, but I don't have time to talk about it. I'll refer you to other talks. Otherwise, if I start talking about this, will be a 5-hour talk by itself. Okay, but basically these issues are real, and RowHammer is a really good example. And today, actually, one of my students is presenting this paper at ASP that is happening in Japan concurrently with this conference that talks about how we should really go about solving it. So it's not solved yet. It's not an easy problem to solve. So how do you solve it? Basically, it's not easy to solve just using technology advancements. You really need to have an intelligent controller that understands what's going on, that tries to figure out whether this is happening and fix it. Again, I don't want to go into the details, but basically you need to have an intelligent controller. So that's not the only scaling issue. We are having other scaling issues. DRAM is not scaling very well. Why not put some other technologies next to DRAM and hybrid or heterogeneous memory? Maybe this could be based on DRAM also, different types of DRAM. But if you look at this picture, this is already happening also. You have hybrid memory technologies where you put different technologies and design the controllers and systems such that you exercise the greens of each technology as much as possible while avoiding the reds of each technology as much as possible. So if you would like to do that, then you need to have an intelligent controller over here again. That intelligent controller needs to understand the properties of the memories as well as the properties of the applications and the access patterns. So this is another example where you need intelligent controllers. Okay, so I will not go into this. But basically, industry is also writing papers about it too. There's a paper from Samsung and Intel from 2014. These folks normally never write papers together. This is the only paper that I could find where they wrote papers together. And it was actually good that they wrote it together. And basically, they said that we're having a lot of difficulty in memory technology. So we should really have intelligent controllers co-designed with memory. Okay. And there are many examples of these intelligent controllers. And we have these intelligent controllers in flash memory chips. So if you look at an SSD today, solid-state drive, it has been there much earlier than DRAM. This is storage, but basically flash memory is a technology that's not very reliable. So in order to make it reliable, you have to have an intelligent controller that understands the characteristics of the technology. And this is our infrastructure, JD's infrastructure, where we actually designed a lot of these controllers to understand these errors. And if you're interested in this, is fascinating. There's a lot of work that has been done, and this is a summary paper that we wrote that talks about how to design these intelligent controllers today. Okay, you may say, okay, that's DRAM, flash, old stuff. This is all the market today, basically, almost. You can say that. But fine, if you're forward-looking, you can say there are other technologies that are interesting. And I absolutely agree. We should be working on other technologies. Unfortunately, you have nowhere to escape, meaning those technologies also need intelligent controllers because they're having problems. I mean, phase change memory is an example where you have to have an intelligent controller to actually manage endurance issues, for example, and other issues. And if you magically come up with some technology that doesn't have these issues initially, as you scale them down to a very small technology nodes, you're going to have these issues. So in the end, in my opinion, there's nowhere to escape. You have to have intelligent controllers close to memory. Okay, so that was the technology scaling part. Now let me pull up to the systems and applications part, and I'll give you a little bit more motivation, and then we're going to talk about some techniques. So I've already said these. Basically, we're having a lot of problems with data, energy, and data moment. I think if you pull back a little bit, in my opinion, we should be even more considerate into the future. Do we want a world that looks like this? Or do we want a world that looks like this? I prefer the first one, I think. Although 1940s Pittsburgh used to look like it. I wasn't there in 1940, so I was there in 2009, so that was much better. But basically, we have a responsibility to the future as computing designers, because the computing power is actually increasing. And especially with the recent announcements of these huge networks, I think we're wasting a lot of computing power to do something potentially intelligent. We'll see if it's really intelligent. We need to think what we're doing, I think. And I think we need to rethink the basic principles of computing. So I would say that we want energy efficiency and sustainability. We cannot give up those, but we also cannot give up performance. So we need to find a way of getting all of them at the same time. And if you want to get all of them at the same time, maybe we should re-examine the decisions that we make at the beginning. And I think I already kind of said this. We already move data between the processor and memory a lot. That causes great energy waste because there's a lot of movement. It also causes a lot of performance loss, but we actually add a lot of techniques to our system to overcome that performance loss. We add heavy auto-order execution, heavy multi-threading, huge levels of cache hierarchies. If you look at the memory hierarchy today, it's most of the system today that we have discussed, and prefetching, etc. And these techniques, sometimes they work. Most of the time, they don't work well enough to overcome the disadvantages they bring, which means that you bring actually additional energy waste, additional complexity into the system. In fact, we presented a paper at Micro in October. And the whole idea of the paper was, you have this huge cache hierarchy in the processor. How do you bypass it? Because the data is not going to come from the cache hierarchy. The data is going to come from the main memory. And we have a machine learning-based, perceptron-based mechanism to predict that. So I like this idea. And this actually won the best paper award at Micro. But if you think about it, if you pull back a little bit, maybe we're doing the wrong thing in the system to begin with. If you're actually developing such ideas to bypass the huge cache hierarchy that you have built. Okay, so I think the fundamental problem is we're processing data far away from the data. And as a result, we're actually making our systems much more complex. And again, I showed you this picture. We focused a lot on the processor. All data gets processed in the processor at great system cost. And when I say processor, it could be a CPU, GPU, accelerator, FPGA. They're all the same. They all abide by this picture, basically. And let me give you some historical context very quickly. We know that memory is a problem, actually. This is a paper that was written by Dick Sykes, who was the chief architect of the Alpha system, which were the fastest processors of their time. After they designed their flagship processor in the 1990s, Dick Sykes wrote this paper titled "Is the Memory Stupid?" He basically said that we've designed this processor to finish 4 instructions every clock cycle. It's finishing 1 instruction every 4.7 clock cycles. Basically, it's operating at about 5%, less than 5% of its efficiency. Why? Because it's waiting for data to come back from memory on a database workload in that particular case. And he basically ends this article saying, I expect that over the coming decade, memory subsystem design will be the only important design issue for future microprocessors. So that's Dick Sykes. This is the data from my own PhD thesis. We worked together with Intel to look at their application that they're designing, their processors for. And basically, most of the time, the processor is waiting for data. Same conclusion. If you're interested, we've written a paper about it. And if you don't believe us or Dick Sykes, since everybody believes Google, there's Google's data from their own data centers, shows essentially the same thing in 2015. In the state-of-the-art processors that are employed in their data centers, in the state-of-the-art workloads that they run, according to them, all of their data center workloads, most of the time, the processor is waiting for data. 10 to 20% of the time, you're actually doing actual processing. Okay, so I think I've harped the point. We have a grossly imbalanced system today, and we have overly complex and loaded processors. As a result, we're very energy inefficient, low performance, and complex. And that's why I showed you this picture earlier. We designed these processors, yet the processors are still bottlenecked by memory, even though we dedicate most of the resources for memory. So let me give you the energy perspective, which is even worse. So about, I think, 8 years ago, Bill Daly gave the keynote at this conference, HiPEAC, and he used the slide. So I borrowed the slide from him. The numbers you can argue with, but the trends have not changed that much. This is the energy cost of a 64-bit double precision floating point operator, 20 at the time, with some technology assumptions, of course. This is the DRAM read or write, 16 nanojoules. That's 800x difference. So the question is, does it really make sense to actually go to memory twice to get 2 operands, do this complicated arithmetic operation, and write the data back one more time to memory, and spend 3 times 800x to do a very simple, energy simple operation? So if you think about those numbers, to overcome that energy differential, you need to reuse the data thousands of times on the chip. And usually we don't have that kind of locality in today's workloads. That's why we want to bypass the caches and get rid of the cache as much as possible also, or put processing next to memory. Okay, so you could argue that 800x is high, and I agree. Usually it's closer to 100 to 200x, but that's still two orders of magnitude. Okay, but that was a complicated addition. That was 64-bit double precision floating point operation. What about that 32-bit addition? You get 6400x difference. between a DRAM access and a 30 bits. And in machine learning today, people are trying to do binary neural networks or 4 bits, 2 bits, 8 bits, whatever you pick. That's much more simple than this operation over here, right? So it's going to be even worse for machine learning applications that try to operate on very simple, small data bits. Okay, you can read more papers about it. As a result, basically more than 60% of the total system energy is spent on data movement on average across these applications, but this number is actually much larger, as I will hopefully show you later on. So I would argue that we do not want to move data. We want to actually move to a computing paradigm where we can enable computation with minimal data movement, where we have options basically to compute where it makes sense, not just the processor, but we should be able to compute inside the cache, inside the memory controller, inside the memory itself, inside the interconnect while the data is moving, inside the storage system, inside the sensor, and inside the camera, wherever the data is generated. So I'm not arguing just for main memory, because this main memory is just part of a bigger system, right? This is the idea of a data-centric system. So, but I'm going to focus on main memory because I think main memory is very, very interesting in today's systems. And arguably, this is one of the hardest parts to modify. You could more easily do processing inside the storage, in my opinion, today. You could more easily do processing inside the SRAM caches because a single company can control the entire chip. But memory and processor are very, very decoupled today. How can we couple them together? It's a harder research problem, in my opinion. And also, there are many applications that are designed to fit main memory today because main memory capacities have improved significantly. So the question is basically, can we design systems where the processor asks the memory, can you process this function or this application or this instruction for me? There could be different granularities. And the memory says yes and returns the results. And then they cooperate somehow. This is still an accelerated type of model. So I think even into the further future, we should really think about completely distributed agents. You have processor and memory, they're equal. Right now, we're going to look at an accelerated type of model where processor is still somewhat the master and it offloads operations. And I think that's a good place to start, in my opinion. So even with this model, there are many questions. How do you design the compute-capable memory and the controllers, processors and communication units, software and hardware interfaces? That turns out to be hard. And then once you go into the system level, how do you design the system software, compilers and languages, and algorithms and theoretical foundations? Because you need to change your algorithms to actually fit this model going into the future. And I think I'll mention the theoretical foundations also, because if you think about the theory of computing, many of you have taken probably courses at some point in your lives about theory of computing. And essentially what you've done is you've counted operations, right? The complexity of an algorithm is determined by how many operations, big O notations, it executes. I would argue that based on what I've shown, that's the wrong thing to do if you want to optimize. Everything else is a big constant, but those constants are huge today. So we should really think about a more data-centric theory of computing where we think about data movement as the first class thing to quantify. And I think this needs to be done going into the future. We don't have a good theory of data-centric computation. And that's one of the reasons I think we're having difficulties in advancing in design of systems that are more data-centric also. And these are chicken and the egg problems also with each other. The reason why compute-centric theory has been developed was because you have compute-centric computers all over the place, right? Okay, so we cover a lot of these issues in our archive paper. If you're interested, you can take a look at them. I'm going to pick and choose some topics over there. But we also have a processing in memory course, which anybody here is welcome to attend. As Jose mentioned earlier, we have all of these courses live streamed. So I think having these courses will enable adoption going into the future also. I will mention that we need to think differently from the past approaches as well. And now we're going to get to a fork in the road, and I'm going to ask you a question. But before that, are there any questions? Or is this all boring? Hopefully not. Okay, now I'm going to ask you a question. So because and we have limited time, I think. Let's see. Okay, but okay. So basically, there are two types of processing in memory, and I think it's good to be clear about that. And these are two general types. Every processing in memory mechanism can be classified into one of these two. The second one is the first one is more forward-looking, and it's going to be harder to adopt. The second one is, I think, already happening. So let me give you the idea. Basically, this is compute units today. This is memory units. And processing near memory says put the compute units logic as close as possible to the memory. At some point, they get integrated. But still, computation is logic. You designed as logic today, and it's integrated into the memory at some point. So this doesn't change the paradigm that much. You can have an x86 processor, for example, integrated inside the DRAM. I wouldn't recommend that necessarily, but you can think of it that way. Processing using memory is fundamentally different. You have processor, memory, forget about the processor. This is memory, say DRAM. I'm going to use DRAM, and this has some fundamental computation capability because of its analog operational properties. I'm going to take advantage of those analog operational properties to actually do computation. So I'm not going to design a new logic like we're doing today. I'm just going to use memory as is, but exploit in a different way. So I think this first one, the second one that I talked about is called processing using memory. You're processing using the analog operational properties of memory. That has not been examined as much, whereas processing near memory was what was proposed, let's say, 60 years ago. So my question to you is, which one do you want to cover first? You want to cover the more forward-looking one, using memory, analog computation, or what's already happening today? I think they're both interesting, but you got to choose. Who votes for processing using memory, analog computation? Okay. Who votes for processing near memory? Okay, interesting. I think I saw more hands for processing using memory.
That's what you want to do.
No, not necessarily. I actually switch these slides sometimes in this particular case. Okay. Let's vote. Based on that information, let's vote again. Who wants to do processing near memory? I would say the second one, which is the okay. Who wants to do processing using memory? Analog. Okay, it's still the same. Sorry, you guys vote. It's not my fault. Okay, so let's talk about this one. I'll try to go relatively quickly because we don't have a lot of time. But basically, the idea here is to use analog operational principle of memory to do bulk data movement and computation memory. You can exploit internal connectivity to move data, and you can exploit analog computation capability. And there are many, many things you can do. And this is actually doable in any type of memory. You can do it in SRAM, DRAM, emerging memory technologies, flash. I'm going to talk especially about DRAM, because I think DRAM is, again, the tough part and also the commercially very interesting part today. I'm going to start simple. I'm going to talk about data copy and initialization. And if you look at applications, there are many data copy and initialization you do. In fact, Google, in their paper that I mentioned earlier, they said that in their data center workload, these two function calls, mem and memcopy, occupy 5% of the execution time. That's amazing for just two function calls. So how do we do data copy today? You basically go through the processor. This is something where the processor doesn't do anything again, right? It's you're copying one location to another location in memory, but you have to do it through the processor today because you have no other option. At least you have to do it through the memory controller. You can also do it through the DMA engine, but it's still occupying memory. In the future, I think we would like to do something like this. Memory, please do this for us and don't disturb anyone else in the system. And that's the idea. And if you do this, you would get low latency because there's ample bandwidth in memory. You don't use the data bus, which is arguably the most important resource that we have, maybe not arguably. No cache pollution, but you can eliminate that today. No unwanted data movement, essentially. And if you do the 4 kilobyte page copy from inside the memory, you can reduce the latency from 1,000 nanoseconds to 9 nanoseconds and energy to 3.6 to 0.04. And the idea is very simple. You can actually do it in today's DRAM chip by wiring timing parameters. Again, Ataberk actually delivered a talk yesterday. Was it yesterday? No, the previous day when I wasn't here on PyDRAM, which is an infrastructure that FPGA-based infrastructure that you can download today, and you can do this in real DRAM chips by wiring the timing parameters. Originally, when we wrote the paper, we didn't think about that, but later people have shown that you could do that. So basically, the idea is you activate the source row, which brings the data into the destination row, which brings the data into the row buffer in DRAM, which are sense amplifiers. You don't need to know about exactly how it works, but the data is very robust in those sense amplifiers. Then you basically do another activation to the destination row, which brings the data from the sense amplifiers to the destination row. That's the idea. You use internally some buffering structures that exist inside the DRAM chips to copy data from one place to another place. And that's the idea. And it works, as I said, in real DRAM chips, most real DRAM chips today by wiring the timing parameters. And I think this is enlightening in my opinion, because these chips are not designed to do this. We're violating the timing to actually do something that they're not supposed to, or at least they're not specified to do. Now, if you can do this, who knows what you can do if you actually design these chips to do this data movement internally. That's the idea. Okay, so this negligible hardware cost. And the performance benefits are significant, and Ataberk actually showed system-level benefits in his talks. Performance and energy benefits, I should say. It's performance and energy both improve. Okay, so these folks actually showed that by violating timing parameters, you can mimic row clone. And then we built on their work with PyDRAM that was presented a couple of days ago. And if people are interested in using this, we'd be happy to support it. Ataberk is committed to supporting it, right, Ataberk? Okay, there you go. Now you have his commitment on record. Okay, and you can also find a lot of information. Okay, these are his results. I'm not going to talk about this because they were presented. Okay, so if you think about it, this is memory as an accelerator right now. We have all these accelerators that are compute-centric. We're building accelerators that are memory-centric, very specialized accelerators, data moment accelerators, right? And we're taking advantage of the internal properties of memory. And I didn't talk about how you can move data from one bank to another. That's also possible. That's not the fastest mechanism. The fastest mechanism is inside the same subarray, basically. Okay, so the question is, can we build other accelerators over here that are more memory-centric? Because these accelerators actually are not bottlenecked by the memory bus like other accelerators have been. These accelerators can be specialized to the requirements of memory, and they also have high bandwidth, low latency access to large amounts of memory, essentially. Okay, so that was data moment. You can say, okay, that's cheating, but we can actually do computation. You can do a bitwise majority function and bitwise not in DRAM at low cost using the analog computation capability of DRAM. And the idea is very simple. Activating multiple rows performs computation, and you get significant performance energy improvements. And you can actually do this on a limited set of DRAM chips by violating the timing parameters again. This is much harder to do because you need to activate 3 rows concurrently, and DRAM is fundamentally not designed for that, clearly. But by violating the timing parameters, these folks from Princeton showed that in a limited set of DRAM chips, you can actually get bitwise AND and bitwise OR. I think this is even more fascinating than row. So the chips are not designed for this. Bitwise NOT is harder because NOT requires a complement and you need some circuit modifications. And new memory technologies enable even more opportunities. I'm going to talk about them. These actually are fundamentally, whenever you read data, the reads are not destructive. As a result, you can operate on minimal data movement. And also you can do other operations like matrix vector multiplications that are fundamentally not possible in current DRAM architectures. Of course, all of these analog operations have reliability issues potentially. Now, let me give you what you can do in DRAM. So these are 3 rows in DRAM. I'm showing only 1 bit cell, but imagine that each row is 8 kilobytes. So you can do this on 8 kilobytes at a time. And imagine that you may have thousands of rows, thousands of these things. So you can actually do this on millions of bits at the same time. It's a bitwise operation. Basically, the idea is to activate 3 rows concurrently. If you do that, the result is the majority of these 3 rows, which is if at least 2 of these cells are charged, you get the charge state at the end over here. If at least 2 of these cells are discharged, you get the discharge state at the end. So final state is a bitwise majority function, which is actually a great function to think about. People have thought about it. People use it in quantum computing in different ways. I don't have time to go over that. But if you take C out, you get the OR of A and B if C is 1. And you get the end of A and B if C is 0. Now you have bitwise AND and bitwise OR. Now you're asking probably, it's not functionally complete. It's not functionally complete, you need a NOT to be functionally complete. How do you get the NOT? It actually exists in this picture. If you actually activate 1 row, you get the data over here and the complement of the data over here. You just need to supply the complement somewhere else. Because of this cross-coupled inverter, you actually have the immersion function already accomplished in DRAM without requiring any other logic. You just need to supply it somewhere, and that's what we do in our work. I'm not going to go over it, but that requires some changes. So now the question is, what can you take it? What applications can take advantage of this? Initially, we looked at applications that are designed for bitwise operations. But again, as I said, more recently, binary neural networks have been coming up, and I think this is a very good fit for binary neural networks. And we have some work that I will mention later on that shows that you can actually take advantage of this with low bit width neural networks as well. But clearly, if the application is designed for bitwise operations, you can make some algorithmic modifications and fit it into this hardware that's bit serial, and that operates on many bits at the same time. And if your application is not, you can still fit it in, except you need a lot more work to do that, to express your application with bitwise operations. And a bitweaving database is a database that was designed for this purpose so that the database can be accelerated with GPUs. And we took it and we actually ported on the mbit system, which we called mbit. And you get significant performance improvements, as you can see over here on the system. These are end-to-end performance improvements on query latency. Okay, I don't talk about energy over here, but you can find results in the paper. So how do you generalize this? This is actually a really interesting substrate. And we looked at working on generalizing it because we don't want to, we want to make it easy for the user. The user should be able to specify any operation over here. This could be a convolution operation. And they could actually specify using AND or NOT logic. And we have a way of converting to majority NOT logic. And then we have a way of optimizing that majority inverter graph, which we don't have time to talk about, and then converting into a microprogram that's executed in the memory controller using these activation and pre-charge operations. Whatever I showed you earlier, triple activation or back-to-back activation of rows to do the copying as well as to do the bitwise operations. So basically, your favorite function, convolution or multiplication or whatever you want over here, can be converted into a microprogram that can be executed by the memory controller. and that can be associated with an instruction that actually triggers that microprogram from the memory controller. And this is the programming model that we're thinking of. You have actually an instruction. When that instruction gets executed, the instruction gets shipped to the memory controller, and the memory controller executes this microprogram to actually execute the instruction. And this clearly makes it easier. And I think there are more works that are coming up on having a full compilation infrastructure for this bit serial computation. There's a work coming up at HDCA this year talking about compilation for bit serial architecture. I think going forward, people will be developing this sort of infrastructure. And if you actually do this, you get even higher performance and energy improvements, which I'm not going to talk about. It's covered in the SimDRAM paper. That was an S+. Okay, so you can say this is bit serial. What if you want to do 64-bit multiplication? Unfortunately, that's not great, of course, because it'll take time. So the idea is, if you want to do a 64-bit multiplication, you should really do many of those so that you can tolerate the latency of 64-bit multiplication. If you don't have any of those, then you may have a problem. So we've more recently been looking at how to do more complicated operations in DRAM. I'm not going to talk about this in detail, but actually you can use lookup tables in DRAM with more modifications to DRAM. This doesn't take advantage of the existing properties of DRAM because it adds a lot more logic to DRAM. But I think going into the future, we should be thinking about these modifications to the DRAM as well. And other stuff that I'm not going to talk about is you can actually have security infrastructure in DRAM. If you start thinking what else I can do in DRAM, you can actually do a lot of things in real DRAM chips today. This is another example in real DRAM chips. By reducing the latencies, you get errors in some of the cells, and some of the cells give errors that you can identify the DRAM chip. So this could be a physical unclonable function. So you can do remote attestation by identifying the DRAM chips. You could use a similar property whenever you reduce the latencies in some DRAM chips. Whenever you reduce the latency, you get unreliable operation, and some DRAM chips fail randomly. So you can actually have a random number generator if you understand which cells provide random numbers. That's actually very interesting. And there's more work. Ataberk presented this work at ISCA a couple of years ago that talks about how to do this more efficiently. And you need to have end-to-end system designs. Okay, so that's DRAM. You can actually do very similar things in Flash. I don't have time to talk about it, and you can take advantage of it, in my opinion. You can actually do very similar things in non-volatile memories. Phase change memory is another example that talks about, this work talks about row clone and bitwise operations and phase change memory. You can do other things in crossbar array-based memories, like resistor memories, phase change memory. And this is actually interesting. I will spend some time to talk about it. But basically, crossbar arrays can be used to perform dot product operations using analog computation capability in these memories. Essentially, you're using Kirchhoff's laws right now. And the bit line current is a sum of the product of the word line voltage plus times the cell conductance. So basically now you have computation, matrix computation. So let me give you an example over here. So you can actually express your matrix, and you can load the values in terms of resistances over here. And then you can input your vector as analog voltage values. And essentially, the results that you get would be the multiplication of the voltage values with the conductance of the value that's encoded as part of your matrix across the bit line. So you can actually have a dot product operation, and there are more animations over here that I don't have time to talk about. But basically, people have been using this to accelerate neural networks, and I think this is a very promising direction. Certainly, there are many papers, as you can see, that are written. This is just my selection of papers that talk about this, and people have been showing very good results. I think this is still a field that's maturing. The difficulty here is to make this reliable, in my opinion. But if you can tolerate some of the analog unreliabilities, this could be a good way of actually accelerating many applications, not just neural networks, but neural networks is clearly a good one. Okay, that brings me to processing near memory. Any questions on this first part, using memory part? Yes, please.
So it seems like that with existing DRAM, maybe update the firmware or whatever memory controller, and you already have a lot of functionality. And you just mentioned that there's some work with the little bit of logic and you get more operations. And so what do you think are like the most promising things that the DRAM manufacturers could add beyond those things to enable as much functionality as possible?
Yeah. So with the processing using memory approach, I think we've already discussed a lot of things, and the rest requires creativity, I think, figuring out what else can you do. And that's something that people are looking into. But they can certainly do processing near memory. They can add additional logic, for example. And I'm going to talk about that also. And people have been adding, for example, multiplication units inside the DRAM. But that doesn't take advantage of processing using memory.
Yeah, well, kind of next future we can do processing using memory and extra logic.
Exactly. So I think basically what I'm arguing for is you really need to do both, in my opinion, if you want to be a truly general purpose and accelerate many things. But fundamentally, these are different approaches. That's a very good point. Okay, so let me talk about processing near memory in the remaining time. So we're still thinking of memory as a conventional accelerator, but now we're going to actually put logic near and near and near memory. And I think here, interesting thing is applications. I'm going to give you a history of what we have been looking at. Graph analytics is very interesting, I think, and we've started looking at graph analytics. And if you look at graph analytics, you get frequent random memory accesses and little amount of computation. And we've used logic layer next to the memory layers to actually accelerate graph analytics using 3D stacked memory technologies. And very quickly, I'll give you the system design. This is basically, I'll call it Q hybrid. It's a 3D stacked memory. You have logic and memory underneath. And we built an accelerator. This is all the simulation, but because we're talking about 2013 here. Basically, you have you offload your graph computation on a distributed system of these 3D stacked memory plus logic chips, and you partition your graph hopefully nicely. Internally, inside each logic layer, you have another distributed system that's essentially a distributed system of cores, and you have simple in-order cores over here. And each in-order core actually updates the memory that is stacked on top of it. And the idea here is this is a distributed system, and we program it as a distributed, meaning that we don't move data unless it's intermediate data. We move functions to the data. So whenever we want to update a graph node, we actually send a remote function call to the node that houses that graph node with the intermediate data, and that remote function call gets executed by that core. So this minimizes the data moment as much as possible. Of course, you're limited by how well you can partition your graph, right? Because as you go off these chips, you will still be limited by the data. But we see significant results. Again, I went through this relatively quickly, but the idea is don't move the data, move the functions to the data, and do some prefetching so that you can exploit the bandwidth of these technologies. And there's a lot of bandwidth actually in the logic layer to take advantage of. If you actually use simple in-order cores, they cannot take advantage of all the bandwidth that's available to them in this kind of infrastructure. Okay, so what are the results? If you look at the system, this system doesn't look like other systems that were state of the art at the time, because you have processor and memory dichotomy in all of these systems. Whereas here, processor and memory are coupled, and you have a distributed system of processor and memory units. And you can see that at the time, we got 8 terabytes per second access to memory aggregated over all of these cores. And the performance results are also quite significant. Average across 5 graph processing algorithms, we get about 13 to 14x performance improvement. And energy reduction is also significant, as you can see. And later work actually improved this. There are works until 2020 or so that built on this, optimized different parts of the system, specialized for graph processing even more. And today you're almost at 2 orders of magnitude performance improvement and 2 orders of magnitude energy reduction. And it's not a trade-off. You improve both performance and energy at the same time. Okay, because you reduce data moment, basically. Okay, that was tesseract. I will skip the in-store genomic data filtering because I want to talk about machine learning a little bit also. But this is all fascinating. Basically, the takeaway over here is that you can filter some of the genomic data inside the storage system with some specialized computation, and you get significant performance energy improvements. Similarly, I believe it's going to be a lot more important going into the future because data sets are growing. We should really be thinking doing a lot more work on the storage side. Memory is interesting. Storage is even more interesting going into the future, in my opinion. In fact, we should really be designing more storage-centric systems with huge data applications. Okay, I'm going to skip this one also. We talked about this a little bit, but here you can actually, by doing understanding where the data moment comes in different functions, you can ship some of those functions that can be executed on the memory side, so that you can actually minimize the data moment as much as possible. And the idea is basically understand your application, figure out which functions are causing a lot of pain in terms of data moment, and ship those to the memory side. And we've done this with Google, and we see that, for example, in the TensorFlow mobile system, there are 2 functions that are causing a lot of data moment, packing and unpacking and quantization, which you may be dealing with. And if you actually ship those to the memory side, you get significant performance energy improvements. Okay, I'll skip some of these. These are all very interesting, but we don't have time to talk about that. And a lot of them actually have similarities to machine learning, like time series analysis, I think is quite interesting, but we don't have time. But I will mention this other work that we actually continue doing with Google, which is looking at their neural network models. And here we really wanted to understand the downsides of the monolithic accelerator designs. So this is a very busy slide, but let me give you the high level. We studied 24 cutting-edge Google Edge neural network models, which consists of these neural networks, as you can see. And we analyzed the HTPU accelerator that's used by Google at the time. And we found out that it's essentially, because of its monolithic design, it doesn't work very well. I'm going to give you some examples, because it doesn't adapt to different, first of all, it doesn't adapt to the memory bottleneck, and it also doesn't adapt to the different communication patterns in these networks. And essentially, it doesn't account for heterogeneity in the models, as well as across the layers within neural network models. And we propose a new framework called Mensa. It's essentially heterogeneous accelerators whose data flow and hardware are specialized for specific families of layers. And the key results very quickly, you can improve both performance and efficiency, energy, by about 3x. And again, there's no trade-off. You're improving both performance as well as energy. And also, it turns out you can reduce the area cost compared to a single monolithic accelerator. And we're designing 3 accelerators. Overall, in aggregate, they're smaller than a single monolithic accelerator because you're specializing the accelerator. Some of the accelerators are very lean because they're actually handling the memory-bound portions of the neural networks. That's the idea. And this paper is published in PACT in 2021. You can find more analysis. Unfortunately, we couldn't release the neural network models because Google thinks that this is very important for them. You can ask them if you're interested. But basically, the takeaway is that there is a huge diversity across the different models. This is just a subset of the models that we looked at. The paper has the full data. You can see that they vary a lot in terms of arithmetic intensity as well as parameter footprints. Some of them have very little arithmetic intensity, as you can see over here, but huge parameter footprint. So those are actually tend to be from LSTMs and transducers, whereas relatively simple neural networks like CNNs are actually more compute bound, if you will. And this also changes within the model as well. So across different layers of a neural network, you can see that there's a huge variation in terms of arithmetic intensity as well as multiplication and accumulation operations. And the idea is, instead of designing a single monolithic accelerator to try to accelerate all of these at the same time, why not design different heterogeneous accelerators to accelerate families of these? And again, the question is, of course, now, how do you discover what are the families? How do you adapt things? I think reconfigurability helps. In this case, we didn't look at reconfigurability, but I think going forward, we need to look at reconfigurability. And there's a runtime system that detects what model or what layer goes to what accelerator. And in the end, we ended up designing 2 data-centric accelerators and 1 compute-centric accelerator. Okay, how to identify where families? There are some compute-centric layers, there are some data-centric layers. And this is a matter of classification, again, in terms of the properties of the layers. And this is some analysis that we did in HTPU. You can see over here that in some workloads over here, especially LSTM and transducers, most of the energy is really spent on the optic interconnect and VR. This is much worse than 60% that I mentioned earlier, right? This is closer to 90%, in some cases, 99%. So you can actually reduce energy significantly by putting the computation next to the memory, as we do in a lot of these models. And this is a throughput improvement that we get. Well, this showed energy improvement also, as you can see over here. The energy improvement is significant, especially in these models, but also true for some of these other models as well. Okay, so if you're interested, there's more in the paper. I covered it relatively quickly. Any questions? Otherwise, I think I'm getting closer to conclusion. Oh, okay, we have. Okay, so let me conclude that. So I think hopefully I've convinced you that we need to revisit the entire stack. But I will mention that adoption is not easy. We need to think about a lot of things. Now, in specialized domains, I think it's going to be easier. But if you really want to do this general purpose manner, you really need to think about a whole stack of issues like this. But I believe all can be solved with a change of mindset. Okay, I think since we're out of time, maybe I'll jump to the conclusion slide and then, oh, if I can. As I said, this could be a 5-hour tutorial, but now we're doing reconfigurability. So my conclusion slide is here. So I think basically I will repeat that we have nowhere else to go, in my opinion. unless we come up with a new technology. I don't know why this is, okay. We must move to some system design that are balanced, high performance, energy efficient, even if we move to new technologies, because we may actually go to a new technology that alleviates some of these issues, but in the end, we're going to end up in the same place at some point. So we'd like to enable computation capability inside and close to memory. This can lead to orders of magnitude improvements, as I've shown you. Enable new application and computing platforms, as I have not shown you, but I believe that this could happen, especially in areas like genomics, where huge data is generated. And I believe actually this can enable a better understanding of nature. Because when I was studying, let's say, psychology about 20 years ago, psychologists were enthused by computers. They said, oh, this is a paradigm for understanding humans. And then they dropped it very quickly because they figured out computers are nowhere close to humans. But I think, because fundamentally computers are operated very differently, right? But I think brains, at least as far as we know, they're really operating with computation and memory intertwined in some way, and communication. So maybe going through this paradigm will enable us a better understanding of nature in the future. So I think the future is very bright, but we need to do research and design across the computing stack. So I'll leave you with this picture at this point. Thank you.
Thank you for the great talk. There's a lot of interesting stuff here. So we have time, we have time for a couple of questions, perhaps.
Thank you for the inspiring talk, Onur. So I have a question that is not it's more, it is weird as well. So you look at the trend on this machine learning work, because the trend is the workloads are more probabilistic, so the algorithms are more probabilistic, and we are all of us trying to solve or run these probabilistic algorithms on the probabilistic training machines. We use whatever we call that. So are we doing something wrong here? Do we look into probabilistic training machines? So this doesn't mean that just compute, right? The compute plus memory, everything. And run the probabilistic algorithms on the probabilistic training. So this is something I'm talking about more on the designing or finding the ways to design the probabilistic training machine. Nobody to raise investigation. This is something we need to put people, especially in the universities, academic.
So that's a great question. I think, I believe fundamentally, I would say yes. And I think hardware is easier to design if you actually can make it probabilistic. The question is, how do you reason about a probabilistic machine? If you need to put effort into figuring out how to reason about a probabilistic machine. In fact, the processing using memory approach that I talked about could be a probabilistic machine, right? I didn't think about talk about it that way, but the analog computation is by nature probabilistic. There's a lot of noise over there. And if you try to make it deterministic, it actually is harder to make it deterministic. If you can actually take advantage of the probabilistic nature of that analog computation that you discussed in DRAM and VM flash, and couple it with the probabilistic applications, I believe you can actually take advantage of things in a much better way. Because there will be additional cost of enabling deterministic computation in those systems that are fundamentally analog in nature. And that's one of the reasons analog computation did not succeed in the 1950s. People wanted deterministic computation, right? If you actually have applications that are probabilistic in nature today, and we can somehow reason about executing them on probabilistic hardware, I would argue that designing that probabilistic hardware in an analog way is much easier. And in the end, you can have a much more efficient system end to end. So that's a long-winded answer, but I think I would argue that we should be looking at those things.
But I don't see many people, even in academia, so there's super close relationship, even in your paper, with industry, that makes you focus on the short term, not the long term. I think that's why I feel that it's missing. So nobody is actually, okay, I'm going to ignore industry. I'm just going to look into, okay, Alan Turing proposed this probabilistic training machines, and nobody is actually investing. Maybe there are some niche research happening somewhere.
I mean, yeah, there is some happening, but yes, I think more needs to happen. I think here the issue is with not necessarily the researchers, but the reviewers, I would say. Because, for example, let me give you my experience with the analog computation papers that we have written. The Ambit paper, the bitwise computation paper, it got rejected 4 times. It got accepted in the end to micro. And I mean, there are many reasons. One of the reasons was DRAM manufacturer will never implement it as analog, etc. Basically, people want deterministic because the mindset. That's why I say we need to change the mindset, right? The mindset is really we want determinism and we want, let's say, no errors in our systems necessarily. And going into some different model that slightly, let's say, can potentially violate that if it's not done very carefully, triggers these things in the reviewer's mindset, in my opinion. Yeah, I think we need to fix that. We can fix it by changing the reviewing practices also in general. We need to be more open to new technologies for sure. Yes.
Well, thanks a lot for the pride. So we changing the mindset. Obviously, the problems there very much with the notion of success and activity at the same time. Everything is intermixed, and it's so difficult that you couple that, and we need to rethink that too. So
you said access and execute, and
well, essentially, reading from memory, compute, storage to memory. Right? Every computer program, every undergraduate is taught, every school student is taught to program like that. Should be teaching something different.
Yeah, I think so. Actually, I think that has been the success of the existing compute-centric model. We teach things like that, but I think we really need to start as early as possible. In my freshman class, for example, I talk about processing in memory. I don't go into detail of it, unfortunately, but it's good to give options to students that there are other models that may exist. So I think it's good to talk about things like data flow, things like processing in memory, saying that historically things have evolved this way, but this may not be the best way of doing things. So opening minds would be very useful.
But you show them that's where progress.
Oh, I think, yeah, I think, yeah, over time, yes. I think it's important to do that. I agree.
Okay. So unfortunately, we don't have more time. So let's run over again for the talk.